Hi, my name is Leen, and on this video I would like to talk about the DAC Peripheral, found on nearly all of Renesas' newest microcontrollers, the RA. In this block diagram we can see the RA2A1 group, shown here on the right. The RA2A1 includes the ARM M23 CPU core with up to 48 MHz frequency. Operating from 1.6 to 5.5 volts, the RA2A1 is offered with 256 kilobytes of flash and 32 kilobytes of RAM. The RA2A1 includes many efficient and unique features. This video will focus on the digital to analog converter, or DAC for short. The RA2A1 is the RA series premier analog-centric microcontroller with advanced 16-bit and 24-bit ADCs, 8 and 12-bit DACs, and integrated op-amps and comparators. This, in addition to a range of serial interfaces including USB, make the RA2A1 a very versatile microcontroller. So what is the digital to analog converter, or DAC? It is a peripheral that translates signals between the digital and analog world, in effect the opposite of an analog to digital converter, or ADC. And just like an ADC, the higher the resolution, the better it replicates the signal. The RA2A1 supports both 8 and 12-bit DACs, giving respectively 256 and 4096 bits of resolution. The output of the DAC ranges from ground to VCC, or the provided reference voltage. The 12-bit DAC converter converts discrete time digital amplitude signals into a continuous time continuous signal. The DAC12 also features an integrated output current amplifier that can be used to drive external loads with high enough current. Additionally, the DAC12 can be configured to operate in sync or out of sync with the ADC. This capability can be used to control the timing of inrush current generated by the DAC and to prevent degradation of the ADC conversion accuracy due to interference. Besides the single 12-bit DAC, the RA2A1 also boasts a dual-channel 8-bit DAC called DAC8. Like the DAC12 or DAC12, it also features an integrated output current amplifier that can be used to drive external loads with high enough current, and it can be configured to operate in sync or out of sync with the ADC. Reviewing the DAC12 block diagram. AVCC0 and AVSS0 are analog inputs that power the block, while VREF-H and VREF-L are the reference input voltages. These can be tied to VCC and ground or an external reference voltage. DA12_0 is the single channel output, analog output of the DAC unit. The integrated charge pump enables the DAC to operate at VCC levels under 2.7 volts, as the RA2A1 can operate down to 1.6 volts. The data registers associated with the DAC are shown. DADR0 contains the value to be converted, while DACR, DADPR, DAVREFCR, and DAPC are configuration registers. The synchronization circuit reduces interference between DAC and ADC conversion circuits. DAC converted data update timing is controlled by the synchronous DA conversion enable input signal from the ADC, which reduces the effect of DAC12 inrush current or ADC conversion accuracy. DAC conversion can be started on input of an ELC event. See my video on that topic. And finally, internal operational amplifiers can be used to amplify small output voltages. Renesas provides an example project bundle for all of their RA evaluation boards. However, these demonstrate most of the peripherals on the device. However, An example of the DAC 12 is currently not included. Therefore, I have configured the following example. The DAC 12 example project for the EK RA2A1, or evaluation board of the RA2A1, outputs a sawtooth that varies between 0 and the maximum output of 4096. A new DAC 12 value is fed into the DADR0 register every time the pre-configured delay expires. This example can easily be ported to other RA devices that also have a DAC 12 peripheral. I will now demonstrate the project on the EK RA2A1 evaluation board. Here we have an example program of the DAC 12 on the EK RA2A1 board. You see that the program has been installed on E-Square Studio with the FSP version 3.0. The stack looks like this. It's just the basic stack with a DAC added to it. The DAC is configured to channel 0 and the output pins are on P500, the DAC 12 output pin. You see here on the evaluation board I have connected an oscilloscope to the output pin of P500, and I have the oscilloscope showing a non-running product. So I compile the project, 0 errors, 0 warnings, and I launch the debugger. And I click run second time, and the project starts running, creating a sawtooth running from 0 to maximum output of 4096. The update frequency can be modified by changing the software delay in the program. The program has been commented to such a way that it's quite easy to port to a different device. This concludes the demonstration. Download the DAC 12 example and implement these features in your next application. This example is included in the downloads together with the presentation. In closing, I would like to thank you for your attention, and if you have any questions or recommendations for future videos, don't hesitate to contact me on this address. Thank you for your time.